Yes, good afternoon all. Yeah. Five, only 4 members, okay, right? Ah, in the previous class we have completed the photochemistry. Today I am going to start the fourth block, that is about the conformational analysis. Okay. Before going to the topic, what is conformational analysis? What is called conformational analysis? There. You know that in several compounds which are having in especially in organic compounds, we see that single bonded compounds, double bonded compounds. Okay. So my voice is audible to you?
Yes, sir.
Okay. Single bond compounds and double bonded compounds, especially double bonded, triple bonds are there. This conformational analysis more concerned about the where the saturated bonds are there. Where the saturated bonds are there means single bonds, sigma bonds. These are undergoing a rotation. CC bond, they are undergoing CC bond rotation. Due to the rotation of that bond, it generates the number of similar compounds, not identical compounds. Similar compounds can be generated. These compounds are known as isomers. These isomers are known as these isomers are generated by the rotation of CC bond. Due to that reason, these are known as rotamers or rotational isomers. These rotational isomers are called as conformational isomers or conformers or rotational isomers or conformational isomers. These conformational isomers, whatever these conformational isomers are there, we're going to study about the physical chemical properties of these conformational isomers or conformers are known as conformational analysis. For example, you take a molecule, it is existing various conformations. Therefore, the study of the physical and chemical properties of these conformations or conformational isomers is called as conformational isomers. First, we are going to give you the definition. What is conformational isomers or conformational analysis? Isomers are also called as conformers. Or rotational isomers are same. Rotational isomers. Rotation of carbon-carbon bond, single bond, carbon-carbon. Or sometimes the single bonds involving rotation, one or more rotations of single bonds Now coming to the unit 16, first unit in that confirmation isomerism or confirmation analysis. Conformations of some acyclic molecules. Right. Then for discussing the conformations of the acyclic molecules, here, if you believe this, this is the acyclic molecule. For example, there is a carbon-carbon bond is there. Such kind of molecules are there. These molecules are known as saturated acyclic molecules. Acyclic molecules. Okay, these molecules are undergoing rotation. Suppose this is the concerned bond we are considering for the rotation. This is undergoing rotation around, suppose, single bond, this single bond, or you can also consider the another bond also. One or more CC single bonds are undergoing rotation, leads to the formation of a new stereoisomers are known as conformations or conformers or conformational isomers or rotamers or rotational isomers. Right. Whenever these rotational isomers are undergoing rotation that leads to the formation of rotamers.
some technical issue. Okay, it's clear now. I'm going to start now again. Yes. This is rapidly interconvertible. These are also known as dynamic stereoisomers. Dynamic stereoisomers. Conformations, that is the conformational isomers, may be defined at different spatial arrangement of atoms or groups in a molecule, arising by rotation around one or more single bonds. Conformers are also known as rotamers. Okay, these isomers are generated due to the CC bond rotation. Due to that reason, we are called it as rotamers. Okay, this is the general definitions and why we need to do this study of this conformational analysis. We need to the compounds and their stabilities. Based on the stabilities, we are going to synthesize it. Whenever we are doing the synthesis, based on the conformational data, we are going to synthesize. Suppose if you want to one particular isomer, whether it is stable or not at that particular conditions, then if it is not stable at that particular condition, we cannot synthesize it. We cannot study their properties. Due to that reason, we need to understand the physical and chemical properties of the particular molecule at that particular condition. What conformational stereoisomer is possible to predict, to isolate, or most population of that compound present in that given sample. Based on that, we are doing the analysis, or based on that, we are going to study of the compounds, right? Here, for the conformational analysis of the acyclic compounds, the important factor, that is the dihedral angle. Dihedral angle is the important word that decides the stability and energy of that molecule, right? Conformers may be defined as dynamic stereoisomers by differing only in their dihedral angle. Then what is the dihedral angle? First, just by the differing their dihedral angle. Then first you need to understand the what is the dihedral angle. Then only we can understand the dynamic isomerism of the conformational isomers, right? Then I'm going to start with the dynamic isomerism, dihedral angle. Dihedral angle. This dihedral angle is indicated with the theta. It is indicated with the theta. We can also write this just simply like this. Also, you can write it like theta. Okay. Then previously I have given a molecule. This is a simple molecule which is containing two carbons. Therefore, it is undergoing the CC bond or one single CC bond. Right. Now, this is the concerned sigma bond which is undergoing reproduction. Then these two atoms are known as A and B are the reference groups or atoms. Reference groups or atoms. Groups or atoms are also called as fiducial groups or atoms. How this dihedral angle will be shown? For example, this is the compound, this is the carbon, carbon bond, right? This is the bond A. This is the bond A. This is the bond B. Right. I'm inserting a plane. I'm inserting a plane. Just look at here. I just choose another color of the pen. Now, I'm inserting the plane which is passing through this bond. Right. I'm inserting like this. This plane is which is passing, and I find usual atom A. Next, another plane which is passing through. I just took. I'm considering the another plane. Right. This is another plane. Now, the angle between these two planes, are known as dihedral angle. The angle between these two planes. Suppose this is the plane A, this is the plane B. Okay. The angle between two planes A and B are known as dihedral angle. Dihedral angle. This dihedral angle, what is the way we can represent it? This is the theta. Dihedral angle theta. Just this is a simple representation, but it will be clearly represented by using the Newman projection formula. By using the Newman projection formula for the same compound. Suppose the compound A, it is attached to carbon, and B, two hydrogen atoms. Okay. This is the other attachments. Right. Right. This is the molecule. When we are going to represent, it is in the Newman projection formula. It is represented in the Newman projection formula. Here, there is a two carbons. Suppose this is the front carbon. Why it is front carbon? The observer or you observing the molecule from this direction. Okay, this is the rare carbon. Front carbon, it is the rare carbon. In the front carbon, the carbon is represented with a dot of the circle, a center of the circle, like this, a dot. A rare carbon is represented by a circle in the Newman projection formula. Now I am taking the circle. This is a circle. The center of the circle is this one. In that, right, this is the front carbon, this is the rare carbon. Then you consider the two 5-hydroxyl atoms. Then the front carbon, a 5-hydroxyl atom is A. Always that should be above the plane, right? Now the remaining two bonds are separated by the 120 degrees. These are the 3 bonds are attached to the front carbon. And another one, the rare carbon. This is rare carbon is a circle. The circle is irregular like this. Okay. Now this is the B. Look at here. The angle between two planes. Look at here. I'm considering the plane which is passing through just take the other color. The plane which is passing through A and 2 carbons and another bond which is present. This is the one plane. It is the one plane. Right. Another plane which is passing through the 5-hydroxyl atom B and 2 carbons and the other substitutions. These are the two planes, right? These two planes, the angle between these two planes, this is the one plane and the second plane. The angle between these two planes are known as theta equal to dihedral angle. Now, dihedral angle is also known as sometimes torsion angle. This is also known as torsion angle. This torsion angle is directional. It is having the directional property. Directional property. Why it is directional? Look at here. Whenever you are taking the Newman projection formula of a molecule, right? You are fixing any one carbon's position of the substitutions A and B, right? At the other substitutions on the rare carbon, you may rotate in the clockwise direction or maybe anti-clockwise direction. These are the directional properties. Okay, if it is in the clockwise rotation, you need to take the angle is positive. If it is taken in the anti-clockwise manner, you need to take it as negative. Okay, therefore, whenever you are representing the isomer, you need to represent this symbol. Whenever you are representing this dihedral angle or torsional angle, you need to indicate these symbols. That's why it indicates whether it is the clockwise rotation or an anti-clockwise rotation. Clockwise rotation or anti-clockwise rotation. For indicating dihedral angle and torsional angle, I am taking one example. This is called designation of conformers. By using the torsional and dihedral angle, we are going to designate the conformers. By using the torsional angle and dihedral angle, we need to designate the conformers. Right. An infinite number of, suppose this one is there, this is the carbon-carbon bond. This is the carbon-carbon bond, a single bond. It undergoes the CC bond rotation. It gives infinite number of conformers. A single fraction of rotation gives the one conformer. Therefore, at the one point, we can rotate any objectives in 360 degrees rotations. 360 degrees rotation. At every fraction, that means we can take the 0.00001 point degrees. Of the degree can generate the one new conformer. New conformer. Right. But the conformations are possible, but however, only distinct spatial arrangements. Why distinct? Okay. Why distinct? We need to differentiate the conformers by which we are going to analyze them. For analysis, we need to maintain some particular rules or standards. Then only we can study their conformational structures and conformational properties. This distinct spatial arrangement resulted by some specific angle of rotation. You need to fix the angle of rotation. Every cycle of that rotation, suppose you take the theta is equal to 30 degrees, theta is equal to 60 degrees, theta is equal to 120 degrees, theta is equal to 180 degrees, theta is equal to 240. That means you need to fix the theta value. That is a dihedral angle. You need to fix it. After the rotating that particular angle, it can generate one particular conformer. Okay. Then compare the initial one and the resulted one. That is called distinction. That means the distinction of conformers. For particularly, you are taking this molecule, this particular molecule, it can rotating the CC bond rotation by 60 degrees every time, 60 degrees rotation. That leads to the six conformers. That leads to the six conformers. How these six conformers are generated, I will show you. Right. Distinguish. A simple designation of conformers. How these conformers can be
Sir, you are on mute.
I'm rotating the molecule in this clockwise manner. That is 60 degrees rotation. 60 degrees rotation of the rare carbon along CC bond. I'm rotating the molecule of the CC bond by 60 degrees rotation. Just I keep fixed the position of the front carbon. I'm just rotating the rare carbon by 60 degrees. Then it results a new isomer. There is no change in the position of the front carbon substitutions. That is the front carbon, and coming to the rare carbon, this B will be moved to 60 degrees. This is the B. Here, the theta is 60 degrees. Now it results structure 2. This is known as para, means it indicates the plus. P means capital P indicates the plus. Para Gauche conformation. Para Gauche conformation. Right. Sometimes it is also called staggered conformation. Staggered conformation. Right. Then you rotate 60 plus I am also adding 60. That is 160 to 160 degrees rotation now from the initial configuration. I'm rotating again 60 degrees. Again 60 degrees rotation. The total rotation is 120. Here I'm going to write in the case of cissoid conformation, here the dihedral angle is theta. That is the 0 degrees. Here there is no rotation. That is also called as torsion angle. Here this is also represented with theta. It is 0 degrees. Next, para-Gaussian or Gaussian conformation or staggered conformation, P Gaussian conformation. Here when we are rotating 60 degrees, dihedral angle is 60 degrees. Here theta is equal to 60. But whenever we are representing the torsion, T-O-R-I-S-N, torsion angle, it is plus 60 degrees. Look at here, this is the directional property. Here we are representing the torsion angle with a directional property. Now I am rotating again 60 degrees. It results the another conformation. There is no change in the positions of the substituents on the front carbon. A, and after rotation of again 60 degrees, this is the B. The total rotation from here to here 120. Therefore, this is known as 120 degrees eclipsed conformer. and the dihedral angle total 60 plus 60. 120 is the dihedral angle. Dihedral angle, that is 120 degrees, and a torsion angle plus 120 degrees. Plus 120 degrees. Again, I'm rotating the molecule CC bond 60 degrees. Again, I'm rotating 60 degrees rotation. 60 degrees rotation. It is in the clockwise rotation, right? Therefore, it leads to A. And whenever we are rotating again 60 degrees, it will lead to this kind of conformation. Right. This is known as anti-conformation. It's known as anti-conformation. Here the dihedral angle is 180 and torsional angle is also 180. Here also we cannot predict the direction because it may be plus or minus. Maybe plus or minus. Both are same. When you rotate the plus rotation, that is clockwise 180 degrees, and when you are rotating the anti-clockwise rotation, it results in the same conformation. That is the reason no need to represent the directional property for the torsion angle at 180 degrees rotation. Right? Then I'm rotating this anti-conformation again 60 degrees of rotation. Then leads to like this. This is known as 240 degrees, 240 degrees eclipsed conformer or conformation. Eclipsed conformer. What is the dihedral angle? Dihedral angle is 240 degrees. 240 degrees. Then whenever I am going to, you are rotating 360. Sorry, 240. 240 minus 360. What is that? Minus 120. Suppose you are rotating the molecule in clockwise rotation. You have required 240 degrees rotation to achieve this conformation. Whenever you are rotating CC bond by the 240 degrees rotation to achieve this conformation. But when you are rotating the molecule in anti-clockwise rotation, it is sufficient to rotate 120 degrees to achieve this conformation. Which one is the lesser one? That will be taken as torsion angle. Therefore, the torsion angle is minus 120 degrees. The torsion angle is minus 120 degrees. Again, I'm going to rotate it 60 degrees of clockwise rotation. Clockwise rotation. That leads to formation of a Metagaussian conformation. This is the A, the B. This is the meta-Gaussian conformation. What is the dihedral angle? Dihedral angle is 300 degrees, and the torsional angle is just whatever 300 minus 360. 300 minus 360, right? That is the minus 60 degrees rotation, right? Just remember that we have 0 degrees rotation. Okay, here you can do that, no need to do anything for identifying the torsion. But at 60 degrees rotation, right, is the direct rotation. Up to 180, there is no doubt, there is no problem. 60, 120, whatever the dihedral angle is equal to torsional angle. Dihedral angle is equal to torsional angle. But after that, whenever you are rotating 240 degrees, that is, you need to do the some calculation. 240 minus 360, that is minus 120 is the torsional angle. Okay, 240 dihedral angle is equal to minus 120 torsional angle. At the same time, at a 300 degrees, 300 minus 360, that is minus 60, that is 300 dihedral angle equal to minus 60 torsion angle. Then, after achieving this meta-Gaussian, this is the torsional angle. What is the difference between the torsional angle and dihedral angle? Definition itself indicates rotation. It gives the initial one. Therefore, this is structure 1. Already given by structure 1. Structure 2. Cissoidally eclipse is the first structure. Paragas is the second structure. And the order. Third one is, that is the 120 degrees eclipsed. Next, anti-conformation. And 240 eclipsed. 5 meta-Gaussian is the 6. Total 6 conformations are generated. Now, in all these, when we're comparing their energies, we can decide which one is stable after substituting the remaining blank substitution. Either with reference to 5 individual atoms, we are deciding what conformation is what, based on the degree of rotation of the dihedral angle and decides the torsional angle, right? These are the designations generally we given for the acyclic compounds conformers. Okay, we have a nomenclature is there that is called Kiliani-Prelog terminology for designation of conformations based on the torsion angle. Okay, after knowing these designations, how these designations are specified for the particular molecule. Coming to the, Klein-Prelog terminology. For designating or for designation of conformations based on torsion angle. Based on torsion angle, we have some guidelines for giving the designations. The first guideline. What is the first guideline for specifying torsion angle? Two hydrogen groups, one on each carbon atom, are required. First of all, for defining, for assigning, for assigning torsion angle, torsion angle. What the main requirement? Two hydrogen atoms are there. That hydrogen atoms, two, one each on carbon. Each carbon, each requires two hydrogen atoms. Two hydrogen atoms are required. Are required. Each carbon, one on each carbon. One on each carbon. For example, you take a dichlorostilbene. This is the, what are the hydrogen atoms here? The two kinds of hydrogens are there, two kinds of phenyl groups are there, two kinds of chlorines. That means that only three different sets of atoms or groups are there. In such case, how to give the, how to assign the hydrogen atoms? For that, this is the guideline A in the point 1. If all the substituents, if all the substituents on a carbon atom are different. Look at here. On the each carbon, hydrogen, phenyl, chlorine. Three different groups or atoms are there. Here also three different groups or atoms are there. The sequence rule preferred group is selected as the fiducial. You need to assign the priority for fiducial atom or group based on sequential rule. Sequence rule. What is the sequence rules? You recollect the rules in the CIP. Con, Ingold, Prelog. Con, Ingold, Prelog. Okay. Look at here in the hydrogen, chlorine, phenyl group. Based on the atomic number, chlorine is the highest atomic number, therefore it gets the highest priority. And the next phenyl group, this is attached with carbon, therefore it gets the second priority. And hydrogen gets the third priority. Similarly, 1, 2, 3. Therefore, the chlorine on each carbon are the fiducial atoms. For the above molecule, chlorine is the fiducial atom for the carbon. Right. This is the first rule, first guideline. Next, second one. Suppose if two substituents in a set are identical, two substituents. Suppose you have take the molecule chlorine, 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 and chlorine. However, the chlorine is having highest atomic number, but the two groups are there. In such case, we cannot decide the fiducial atom on each carbon by using the sequential or sequence rules. In such case, you violate the sequence rule. Just give the fiducial priority to the low priority group. Suppose here 1, 1, and 2. The second one, hydrogen is the least priority group, but we are unable to give the priority to this least
priority group based on the sequence rule. But we cannot decide the 5-divisional atom by using the more priority groups. In such case, the sequence rule is avoided or void. If two substituents, in a set are identical, the non-identical, these two are identical. This one is the non-identical. Non-identical group is selected as group is selected as 5-divisional atom irrespective of sequence rules. Irrespective of sequence rule. Right. For example, in this, two chlorines are having the same priority. Therefore, sequence rule is avoided. Only hydrogens are 5-divisional atoms. Hydrogens are 5-divisional atoms. Similar case, if you use hydrogen, two fluorines are there, the methyl group is there. You consider the methyl group is the 5-divisional group. Okay. Next, third rule. Third guideline in the first rule, that is the C. If all the substituents
Sir, unable to hear you.
Unable to hear. Okay, thank you. You take out of the 3 atoms on the carbon, all are same. You can pick any atom, any 2 atoms on each both the carbons, or for each carbon you can select any one atom. That makes less value of torsion. The torsion angle means a torsion or dihedral angle. But dihedral angle is smaller, that it becomes the torsional angle. Okay, whenever you are selecting these atoms or groups, that makes the lesser torsional angle. That in that way you need to select. Next, you need to assign the prefixes whenever you are giving the designations. Second guideline. In the first guideline, we have discussed 3 sub guidelines. Following prefixes and terms are used for the designation of conformers. For example, whenever you are assigning the torsional angle, you need to give the directional property. Use the plus and minus for the rotation. For the rotation. Of clockwise and anti-clockwise respectively. Next, you can use the other terminology, that is sin for a value of 0 to 90 degrees rotation, and anti for a value of 90 to 180 degrees rotation in both the directions. In both the directions, you can use sin and anti. The sin and anti can be used. Suppose this is the 180 degrees rotation, 180 degrees rotation, right? Now from this is the point of 0 degrees, 0 degrees. Up to this is the 90 degrees. And again, I'm divided it into, okay. What is that? Up to this 180 degrees, 45, 90 plus 90, 90 plus 90. Up to this 90. Sorry, this is the 180. Again, we are going to back to 90 degrees in the reverse direction. This is the plus direction, it is the 90, and minus direction, it is the 90. It is the 180. Suppose if you calculate, it is almost 290 plus 270 degrees rotation. 270 degrees rotation, right? But not necessary to indicate this. Okay, minus 90. Then I'm making the circle here. I just making the circle. I just make the circle here, right? Now in that, first time this bisects into 2 equal halves. At this is the 90 degrees rotation. Suppose this is the 0 degrees. This is the 90 degrees. This is the minus 90 degrees. Right. I'm making the difference to every 30 degrees. It is the, suppose this is the 60 degrees rotation. This is the 60 degrees rotation. This is the 60 degrees rotation. I make it into difference with 30 degrees rotation. Right. Similarly, it is the 90, 60 plus 30, 90, and again 120, 120, 150, 180, reverse. Again 150, 120. Just make it into divide into 6 parts. Make it divide into 6 parts, just like this. I'm using right. Right. Now look at here. This is the 30 degrees, that is minus 30 anti-clockwise rotation. This is the clockwise rotation. This is the plus 30. Suppose here 30 degrees plus 30. This is the plus 60. This is the plus 90. And this is the plus 120. This is the 150. And plus 180, plus or minus 180. And minus 150. And minus 120, minus 90, minus 60. For our understanding, it's not equally distributed, but you understand that. Okay. From this 0 to 30, plus 30 or minus 30. This is indicated with from all these places. This is the periplanar. Okay. Above part is called as syn plane. As syn for 0 to 90. From the positive or 90. 0 to 90, 0 to 90. This is termed as all the area syn. Therefore, this is a syn area, syn. Okay. But it is there is no directional plus or minus here. You can indicate syn. It is the plus 30 plus 30 syn. And this area is particularly called as periplanar. From plus 30 to minus 30 is called periplanar. Here syn means, S means syn. And this is the anti. This area is called, these 3 parts are called anti. A means anti. This is the A, small a, small a. Right. Now this P indicates periplanar. Periplanar. Why periplanar? It is approximately aligned to 0 degrees. That is named as periplanar. Very near to the 0 degrees. That is the reason it is called almost planar. That is periplanar. Therefore, this position is called syn periplanar. SP means syn periplanar. Syn periplanar. Now, after that syn periplanar in the positive direction or minus direction, this is the incliner or synclinal. This is the plus synclinal. This is called minus synclinal. Plus synclinal and a minus synclinal. In the similar way, we are coming to the anti. This is the periplanar again. Anti-periplanar. It is almost equal to the 180 degrees rotation degrees. Therefore, it is anti-periplanar. It may be plus or minus anti-periplanar. In the anti-clockwise direction, it is called anticlinal. It is a plus anticlinal, minus anticlinal and a plus anticlinal. Right. Here I'm clearly indicating that minus 32 plus 30, that is called plus or minus syn periplanar. Syn periplanar. Next, from plus 32 plus 90 plus synclinal. Synclinal. If it is the plus 92 plus 150, it is called plus anticlinal. And plus 152 minus 150, it is called as, just to okay, minus 152 plus 150, it is called as plus or minus anti-periplanar. Anti-periplanar. Next, minus 152 reverse, minus 92 minus 150, it is called minus anticlinal. Right. From minus 32 minus 90, it is called minus synclinal. Next, all are covered. That bit 6 parts are there. Syn pluriplanar plus or minus, synclinal plus, that is plus 32 plus 90. Anticlinal, that is plus 92 plus 150. Plus or minus anti-periplanar, that is minus 152 plus 150. And anticlinal, that is minus 92 minus 150. And minus 132 minus 90 is called as synclinal. Based on that, we are going to give the designations. Syn or anti, the designations are generally given. Then when it is the synclinal equal to the cissoid, or when it is paragashi, when it is metagashi or eclipsed, the table can be represented here like this. For example, torsional angle. These are all known as torsional angles. A minimum angle, if you are represented is in the form of dihedral angle, it will be higher values. But all the values are in between the plus or minus 32 plus or minus 180. Right? Torsional angle. Right. Take the torsional angle. Designation. These are the designations. Designation. Symbol. And reference to the suppose you take the molecule CH3, other substitutions are there. CH3. Here the two methyl groups are the hydroxyl groups. Dihedral angle. Dihedral angle, that is as a multiple of 60 degrees. Right. 0 plus or minus 30 degrees. What we call it as syn periplanar. Generally plus syn periplanar, not the minus. Syn periplanar. And a symbol is represented with the in common SP, but in most of the books, it is also represented as plus or minus. We can also represent it like this. Either both are correct. Okay, then reference with respect to these two hydroxyl atom, this is called cissoid eclipsed. Cissoid eclipsed. That is the conformation 1. And the dihedral angle is 0. Next, plus 62 plus or minus 30. Plus or minus 30. That means minus 30, it gives this 30 degrees. Plus 30, it gives the 90 degrees. That means plus 32 plus 90. That is called synclinal. Synclinal, that is indicated by the plus SC, synclinal. It is the Paragache conformation. Paragache, that is the second conformation. That is number dihedral angle is multiple of 60. 1 into 60, that is 60 degrees. It is the 0 degrees, multiple of 0, multiple of 1, that is the 60 degrees. if you take 180 degree, 120 plus or minus 30. That is the torsional angle. Plus 120 plus or minus 30. This is called anticlinal. This is called anticlinal. It is designated, symbol is AC plus AC plus AC. It reference with respect to the two 5-diazyl methyl groups. That is the 120 eclipsed, 120 degrees eclipsed structure. It is the third structure in the previous representations. It is the multiple of 2, that is the almost 2 into 60, 120 degrees. 120 degrees. Next, 180 plus or minus 1, just no need to represent it. 180 plus or minus 30. Plus or minus 30. That is anti-periplanar. Minus 30, it is the 150 plus 150 plus 30, that is the 10 to 10 degrees. That is anti-periplanar. Anti-periplanar. And suppose here you need to use the plus or minus. If it is the plus 180, you need to take minus 30. Minus 180, you take plus 130. Then only you will get the good value. Plus 180 minus minus 30, that is the plus 150. Minus 180 plus 30 minus 150. That is the way you need to consider. Next, this one is anti-periplanar. It is represented with the plus or minus anti-periplanar AP. It is the conformation is anti-conformation. It is the fourth conformation. It is the multiple of 3, that is 180 degrees. Next, minus 120 plus or minus 30. Plus or minus 30. That is known as anticlinal. Anticlinal or minus AC. It is known as 240 eclipsed conformer. That is the fifth conformer. It is the multiple of 60. 60, that is the 240 degrees. That is the dihedral angle. Next, minus 160 plus or minus 30 degrees. All are degrees values. Right. Now this is called synclinal minus synclinal minus SC. This is called meta-Gaussian, M-Gaussian. Here the M represents the minus. Gaussian conformer. It is the sixth conformer. It is the multiple of 5 times. That is the 300 degrees of rotation. That is the dihedral angle. Okay. The designation of conformers are sin of torsion angle in its remains unchanged, whether the molecule is viewed from the front or from the rear. In the first case, the torsion angle is measured from the A to B, whether here the A to B are methyl group, suppose them from methyl to methyl. In the second case, the observation, we are viewing the molecule from other methyl to, suppose the methyl 1, methyl 2, you are representing like this, whatever the compound you are taken here is, this is the first methyl, methyl 1, methyl 2. Okay, suppose you are viewing, this is the front view. You are observing the torsional angle from methyl 1 to methyl 2 in both the cases. Suppose you are viewing the molecule from the other side, rear side you are viewing. Now this methyl position becomes the, or this carbon becomes the front carbon, this becomes the rear carbon. in both the direction, you the molecule in any direction, these conformations will give the same. Okay, the torsional angles will give the same. Okay, if suppose if the molecule is a synclinal, you are viewing the molecule from this direction, it gives the conformation is synclinal. The same conformation is given by the rear side view also. Either you are viewing from front side or rear side, the conformation is, suppose that is the synclinal, that becomes the synclinal in either directions, right? Next, stability of conformer. How this, then stability of the conformation or conformer. Then I think the second class time is okay, already 3 now. Okay, I'm sorry. Then concluding the session today. You have the then last class today. I think most that is waiting. Okay. We shall begin this now. Thank you. Have
Sir,
any
do we
doubts?
have the last class in the same link?
Yes. No. You have the what is the class has taken by the Mozart previous class? The paper 8 or paper 7? What is the class sir has taken in the previous class?
7, sir.
Then you can join the paper 8. Okay. Or otherwise, Mohan sir will intimate you, no problem. Okay, any doubts? Yeah, it is the more conceptual topics. Okay, you need to prepare for examination very specifically. Some important questions I will give you. Based on that important questions, you prepare for that. Okay, I think this is the last class today. I will send you some important questions in the paper 5 and some paper 6, paper 7. Okay.
There one small dot
Yes,
at the
yes.
top.
Regarding the subject, you can ask.
Yes, sir. The subject only today's class. At the top about rotation, you have showed us 6 rotational structures, isomers. Sir.
Yes, this one.
Yes, sir. So
Yes.
this is with clockwise, sir. Right?
This is with the
Clockwise rotational.
yes, clockwise rotation.
So at the top, if you go a little bit more, it is showed as if it is clockwise, it is plus, and if it is anti-clockwise, it is minus.
Yes, you are indicating the red angle with the minus, but when the dihedral angle you are mentioned, that is the directionless. Suppose you are rotating the anti-clockwise. Suppose this
Yes.
is the 0 degrees, right? You are
Yes.
rotating the CC bond in the anti-clockwise by the 60 degrees. By
Mm.
60 degrees. In such case, you need to deduct the value from the 360. 3 has
Okay.
360 minus 60. That is the dihedral angle. But the torsional angle is what? Torsional angle is in the anti-clockwise, that is the minus 60.
Okay.
In that way, you need to understand.
So then the dihedral will become minus and torsion will become plus.
No.
Hmm.
Dihedral angle is the directionless. There is no directions, plus or minus. Okay.
Okay.
You need to consider only clockwise rotation, whatever the conformer that attains the value, the same value in the anti-clockwise also.
Okay. Got it.
Suppose if it is in this case, it is the 0 degrees dihedral angle is. You are rotating 60 degrees in the anti-clockwise. What is the conformer you obtain? This is the conformer.
Yes.
This is the conformer you are obtaining. Then what is the dihedral angle? Dihedral angle is 300.
Yeah.
300. Okay.
Yes.
But the torsional angle is 60 minus 60.
Yeah. We need to calculate with the dihedral and the present.
Dihedral angle is directionless. Therefore, whenever we are considering a rotation in case of dihedral angle persuasion, you need to consider only clockwise rotation only.
Okay.
Whatever the dihedral angle values are obtained in the clockwise rotation, that the same values, the same conformation will give the same value.
Okay.
After 60 degrees rotation of anti-clockwise, what conformation we got? Meta-Gaussian. Yeah. M
Yes.
Gaussian. What is the M Gaussian dihedral angle? Always 300. There is no change.
Hmm.
But torsional angle will be changed. -60.
-60. Yes.
That is the reason for the differentiation, torsional angle concept is introduced.
Okay, sir.
Differentiation only the torsional angle concept is introduced, right?
Yes, sir. Understood, sir. Thank you.
Right. I think you are followed.
Yes.
Yes, thank you. Any others? Right. Okay. I'm going to conclude the end of the session. Thank you.
Sir,
Yes, tell me.
if possible, can you send this sheet in the group, sir? As I was listening with concentration, I could not make it known.
Right. Okay. These running notes.
Yes, sir. Running notes
I will
today.
send. No problem. I will send it.
Okay, sir. Thank you.
All right.